one last problem that we can look at with respect to our sum and difference formulas. We want to try to find the exact value of the sine of the arc sine of 1/3 plus the arc cosine of -2/5. And we're not going to use a calculator for this, right? Now, this is a question you might remember from the previous chapter where we took a look at inverse functions. And what we're going to do is, let's say that this is going to be equal to a. So let's say a is going to be equal to the sine arc sine of 1/3. What that means is that the sine of A is equal to 1/3. And let's let B equal the arc cos of -2/5, which means that the cosine of B is equal to -2/5. All right, so now we can go ahead and draw our triangles and be able to figure out the remaining sides for these, okay? And the whole reason we want to is, remember, we're going to use a double angle formula in this. So remember, we're calling this A, and we're calling this B. And so in reality, what we have is we have sine of A plus B. And if you remember on our formulas, that's sine, it's going to be sine A cos B sine A with a plus in the middle there. Okay, so let's just hold on to that. That's sine A cos B plus sine B cos A. Or sorry, cos. I think it should be cos A technically, the way it's written. So cos A sine B. Okay. All right. Now, the other thing we have to concern ourselves is what quadrants these are in. Okay, so this one's easy. Remember that the arc sine function, okay, so remember arc sine only lives in these quadrants, okay, so sine minus 1 of x, okay, it's positive here and it's negative here. And if we have the inverse cosine or arc cosine, remember that only lives in quadrants 2 and 1, and it's negative in quadrant 2 and positive in quadrant 1. And so what we're looking at is that B is in quadrant 2. Okay, so B is in quadrant 2, and A is in quadrant 1. Okay, and we're going to have to remember that because when it comes time for us to be able to um, use the signs for this, okay, that might differ, okay, or that might just change like what our signs are going to be. Okay, so let's figure these out. We have our right triangle. Okay, so let's call this A. Okay, remember the sine is the opposite over the hypotenuse, and to figure out what that is, the missing side, we're going to say 3 square equals 1 square plus b square. 9 equals 1 plus b square. 8 equals b square. And so that means that the square root of 8 is equal to b. But remember, 8 can be written as 4 times 2. All right, and so that means 2 roots of 2 is equal to b. All right. Now over here, let's call this b. That's going to be the adjacent over the hypotenuse, right? And so that means we're going to have 5 squared equals 2 squared plus our side b squared. 25 equals 4 plus b squared. 21 equals b squared. So square root of 21 is going to be b, and that we can't simplify. All right, so now let's go ahead and find our sine A cos B. Now we know what sine of A is, okay? Sine of A is 1/3, okay? So remember, we're trying to find sine A cos B plus cos A sine B. All right, so sine of A, we already said was 1/3, and I think we already had the cos of B was -2/5, right? So that's right here. So that's 1/3 times -2/5. The cosine of A, and remember, A is in quadrant 1, okay? Everything's positive in quadrant 1, right? So remember, we have our all students take calculus, all right? So everything's positive in quadrant 1. We're looking for the cosine of A, which is the adjacent over the hypotenuse. So that's going to be 2 roots of 2 over 3. That's 2 roots of 2 over 3. And then the sine of B. Now remember, B is in quadrant 2. but the sign is positive in quadrant 2. Okay, so sine is opposite over hypotenuse, which is going to be root 21 times 5, or root 21 over 5. And so now if we simplify this completely, 1 times -2 is -2. And then we have 2 roots of 21, or 2 roots of 2 times root 21. So that is going to give us 2 roots of 42, okay, divided by 15, since both of the denominators are 15. I do not believe that there's anything that we can do to simplify, since 2 and 15 do not share a common factor. The only factors of 42 are 14, 3, what else do we have? We have 6, 7. All right, so 2, but none of those are perfect squares. So this is as good as we can get with this. Okay, and so that's how we can use this sort of idea to be able to get an exact value using our inverse trig as well as our sum and difference formulas. Okay, so that's the last problem that we have for these sum and difference formulas. There are a number of other sorts of formulas that we're going to look at. A lot of them are going to be in the next section, which is going to be 5.3. So we're going to be taking a look at a double angle formula, we're going to be taking a look at half angle formulas, and we're going to be taking a look at power reducing formulas in that section.